Hi, welcome to Real-Time Music and Sound with Pure Data. I'm Andrew Brown. In this episode, we're going to be looking at oscillators. So let's start with some diagrams. So these are the sort of standard kinds of oscillators that you might find in a subtractive synthesizer. A sine wave, square wave, triangle wave, and a sawtooth wave. They produce different kinds of timbres as a starting point for subtractive synthesis. So today we're going to be looking at creating these kinds of oscillators in Pure Data. We know how to create a sine wave oscillator or a cosine oscillator. The standard oscillator function does exactly that. So let's just create one and have a listen. Got a multiply object as a volume control, DAC as the audio output. We will, oops, not a symbol, we will put a number box above in order to specify the frequency, and we'll put a number box into the multiply to specify the volume. I'll restrict the range from 0 to 1. Alright, so we turn the volume up, increase the frequency, and there we are. We have our sine wave. You can see it on our oscilloscope, and you can see in the spectrum analyzer there's just a very sharp peak right at that frequency, which shifts as we go. The other thing we might do is to use our own sort of PD based oscilloscope in addition, just because seeing the waveform is particularly important in this example. So we're going to use an array to do that. I'm going to call it $0 display. I'll make it 1,000 elements long, use a polygon drawing algorithm and say OK. So there is a display. We need to get our signal to that display. We use the tab right tilde object and we pass it the name of the array. So that audio output can go to there. In order to make that display, we need to send it some bangs. We'll use a metro every 100 milliseconds. And we need to start the metronome with a toggle. Alright, so this is all our infrastructure. Turn the volume up so we can see our display here as well as on our oscilloscope. Alright, so far so good. In fact, what I might do is just connect that directly out of there so we bypass the volume so it's always showing at maximum. Alright, so that's our sine wave. So let's move on to some other waveforms. So from here we want to be able to create other waveforms. We will start with a square wave. We're going to use the oscillator as the basis for our square wave. There is no square wave object in PD. So we're going to just do some processing of that. We can use an expression tilde box to do some math on the oscillator. We know the oscillation goes above and below 0, around the 0 mark, up to +1 and down to -1. So what we want from a square wave is it to go from the extreme of +1 down to the extreme of -1. So we're going to say if the value of the audio input is greater than 0, then output the value 1. So that means whenever it's above the line it'll be all the way up, otherwise make it be -1. And let's connect all that up. And we have a square wave. It's possibly a little hard to see there, but I can show it at its reduced loudness there. So you can hear the square wave is quite a bit more rich than the sine wave in its spectra. We can see that on the spectrum analyzer, lots of harmonics being produced by this square wave. It's because of the angular shape which tends to give us a bright sound. Another waveform like the square wave which we often have is a pulse width. If we look at the square wave again, you can see it's very even in terms of the amount of up and down. A pulse width has a different amount of up to down, the proportions change, and that gives us some slightly different sounds. We can do that by adjusting where the value of this is, and rather than look at 0, which is always the halfway mark, we can, for example, say, well, give us that at 0.5. You can hear that sounds a little bit different. You can see visually we've got only a smaller part going up and a larger part going down. In fact, it's 25% up and 75% down. And we can change that to some other value, say 0.1. .01. All right. And this particular value can also be changed by a variable. So if we put $F2, we take a floating point value in the second inlet, then we can change that cutoff point like so, and you can see on my oscilloscope over here we're getting a difference. Let's show it as well on our own. We're changing the width of that pulse width and getting a change in timbre. So that's from a square wave, which is a 50-50, through to a pulse width, which we can vary from here. So another kind of wave that we can have is a sawtooth wave. What I'll do is I will leave all of this over here. We can connect it back up if we want later on. And we can introduce a new oscillator, which is the phasor object. Now, the phasor object also takes a frequency, but we'll see that one of the differences with the phasor object, when we turn it up, okay, so it effectively looks like a sawtooth, and you can hear that it has its own characteristic timbre, so that's all good and well. However, this sawtooth wave from the phasor, you can see that all of the values are positive, so it starts at 0 and goes up, so it's a unipolar sound. What we really would like is for our wave oscillator to be going all the way from -1 all the way up to +1, or to be bipolar. So we're going to have to do just a little bit of math on our phasor to get it to do that. We'll first of all increase its amplitude so that it goes, instead of from 0 to 1, from 0 to 2. If we look at that and turn it all the way up, in fact, well, if I just display it rather than make it loud in our ears. Okay, so we can see that it's now going from 0 up to 2. So that's partly what we want, but we don't want it to be clipping like that. So we subtract 1 to pull it back inside the range that we want. You'll hear that the timbre is much the same, but now we've got a bipolar sound covering the appropriate range. We can change the frequency, and so there we have our sawtooth wave. So another kind of waveform that we might want to have, I'll leave this one around, this is our sawtooth wave. Another kind of wave we might want is a triangular wave. We can use the phasor as the starting point for our triangle wave, because you can see it's kind of quite angular, but instead of it going up on an angle and straight down, we needed to go up on an angle, oops, mistake, up on an angle and down again on an angle. So we need to also do some math on this particular thing to make that work. So again, we're going to use the upward part and leave that alone and say whenever that value is greater than half, so when we get halfway up the waveform, we want it to actually start going down, do the inverse. Otherwise we can leave it going up. Okay, so our phasor comes out there into the expression box is passed there. Let's give it a frequency, let's give it some amplitude, and let's visualize it in our display. Okay, so we can hear the sound. It's kind of this got a bit more harmonics than a sine wave does, but not as much as something like a sawtooth or a square, which is why it's often used in synthesizers. But at this stage, again, we've only got a unipolar sound, and the amplitude is only 50% of even that unipolar range, so we need to do some scaling to get it into our full range. So we will multiply it by 4, and when we do that, if we visualize it, you got to see that it's a full range, but again it's offset, DC offset, so we need to subtract 1 from it to bring it back down into range. And there we have our triangle wave. Alright, so they're all of the main kinds of waveforms that we find in like a standard subtractive synthesizer. But we can go one step further and display a kind of arbitrary waveform, and for this I'm going to move this down here, and we're going to basically do a waveform, a wavetable oscillator. So to do our wavetable oscillator, we're going to need an array which is going to hold our waveform. I'll call it waveform 1. I'm going to give it a particular size, 259. Seems like an odd number, but the waveform is going to be read by an object called the tabosk read 4, which is doing a 4-point interpolation. So we need the size of the array to be a power of 2, so let's say 256 plus 3 pixels, and that will do the appropriate wraparound size. There's our waveform 1 table, so we're going to be reading from that. In order to read from it, we'll use the tabosk4 object, and we need to tell it the table that it needs to read from. That will then go out to our output, and we need to give it a frequency to read. So now you see at the moment the waveform is a straight line. If you recall, we can draw onto that any arbitrary waveform, and then we can change our frequency. Got it the wrong name, sorry, typo. Easily done, sorry about that. Okay. And so now, as we draw, we can specify the frequency, and this becomes our wave. We can get, you know, waves like kind of square wave that we had before, or any kind of silly arbitrary kind of waveform. So that's very, very handy. But any arbitrary waveform can kind of get a little silly. So there's a few ways in which we can pass arguments to this array. We can do that by using a message box. And if we want to send an internal message, we start with a colon, and then say we're going to send to our array waveform 1. If we send it a constant value of 0, when I click on here, you'll see that it sends just 0 across the entire waveform, which effectively will make it silent. We can try another message, and again we're going to send it to waveform 1, which is that table. This is called the sine sum, which basically sends like a sum of sine waves to that table. It needs to know the size. It's going to be 256, and I can send it just a single sine wave. Sine sum, what have I done here? Sine sum. Okay, like so. If we have a listen, we're just getting a sine wave. Sine sum works such that we can pass it the volume of subsequent overtones. So if I say 0.5 for the next one, then we get that, and then I might go 0.25 for the next one, and we're getting an increasingly complex wave. One of the downsides here is that this waveform, the sum of all these sines exceeds, and we get potentially some clipping here. So we can pass it another command, waveform 1, which is normalize, which will make that waveform fit in terms of its size down to 1. And now our waveform is normalized here and just works like any other wave. We can still mess with that waveform, or we can click to reclaim that. If we wanted, we can add more things, and I've got so the values which are provided for an example very similar to this from the Floss manual for PD, which is very good, by the way. You should check it out. And this is all of the sort of overtone series, which will give us a much closer approximation to a Sawtooth wave. The good thing about this Sawtooth wave is that because it's made up of sine waves, it doesn't have as many high frequency spectra and won't produce quite as much aliasing. Okay, there's just one more thing that I'd like to show you as well when we finish on our oscillators, and that is often in synthesizers there is more than one oscillator, and there's a good reason for that, because we can get a much richer sound if we combine two different oscillators. So let's say, for example, that I duplicate this wavetable oscillator. So I'm going to send that as well, and then we can have a different frequency. So we now got two oscillators. So one thing which we can do is, if I have a single source of the frequency and pass that to both those, then they'll be at the same frequency, which doesn't get us quite as far as we really want to go. There's one more trick, and we can do some detuning. So if I make the second oscillator slightly different to the first one, so it's almost the same, but let's say multiply it by 1.01 times the frequency, and you can hear that we're getting the waveform is phase cancelling against itself, and giving us this kind of pulsing effect, which is due to the amount of detune. I can decrease the amount of detune, so we're just getting this sort of rich phasing effect. Which gives us quite a rich timbral effect as we go. So that's been a whirlwind tour around different oscillators. We started with the sine wave, then we went and produced a square wave, and then turned the square wave into a pulse wave. Then we looked at doing a triangle wave from the phaser, and then converting the phaser into a triangle wave. Sorry, we got a sawtooth wave from the phaser, my mistake, and then converted that into a triangle. We then looked at being able to draw arbitrary waveforms and oscillate around them using the TabOSC4 object, sending that waveform some sine sum combinations to give it a more rich sound, and then looking at detuning two oscillators to give us an even richer sound. So have a go at all of that, and I look forward to seeing you in the next video.